Hello students, today we will start angular momentum of particle. For this, the angular momentum of particle, just as the moment of a force is the rotational analog of the force, the quantity angular momentum is the rotational analog of linear momentum. We shall first define angular momentum for the special case of a single particle and look at its usefulness in the context of single particle motion. We shall then extend the definition of angular momentum to system of particle including rigid bodies. Like moment of a force, angular momentum is also a vector product. It could also be referred to as moment of linear momentum. From this term, one could guess how angular momentum is defined. We will define the angular momentum in this way. The angular momentum L, or the moment of momentum about an axis of rotation, is a vector quantity whose magnitude is equal to the product of the magnitude of momentum and perpendicular distance of the line of action of moment from the axis of rotation, and its direction is perpendicular to the plane containing the momentum and the perpendicular distance. We'll consider here a particle of mass m. Suppose a particle is kept over here, this point you will see, okay, and suppose this is the point A and the position vector of point A from origin is r. So we are considering here a particle of mass m and linear momentum p at this point, which is equal to mv at a position r relative to the origin here. The angular momentum L, you will see that the angular momentum L of the particle with respect to origin O is defined to be L equal to r cross p. Okay, this is the cross product of r and p, where r is the position vector where the point is, and the linear momentum p is the linear momentum. The magnitude of the angular momentum vector is L equal to rp sine theta, where p is the magnitude of vector p, that means the linear momentum, and theta is the smaller angle between r and p. R sine theta, you will see that this is the r sine theta. If you just take this angle, look at here, this is the point A where the momentum is working in this direction and the position vector is located in this direction. The angle theta is here, so this is also angle theta, and if just making 90 degree, if you draw perpendicular here, and which will just meet to the line of action of this linear momentum, okay, so this will be the r sine theta, and the r sine theta is the perpendicular distance of directional line of p from the origin. Okay, so here you will see that if theta, this we expect the angular momentum to be 0, this would be 0, okay, when if the linear momentum vanishes, that means the magnitude of p is equal to 0. If the particle is at the origin, that means r equal to 0, or if the direction line of p passes through the origin such that theta is equal to 0 degree or 180 degree. Okay, so this is about the angular momentum. Next we'll see the relation between the angular momentum and the moment of force. Now we will see relation between torque, moment of force, and angular momentum, which is also called moment of linear momentum. So basically we are looking the relation between torque and the angular momentum. The physical quantities moment of a force and angular momentum have an important relation between them. It is the rotational analog of the relation between force and linear momentum. As we know already, the rotational analog of force is torque and the rotational analog of linear momentum is the angular momentum. So obviously if we are looking the relation between the torque and the angular momentum, so it will be the rotational analog between the relation between the force and the linear momentum. And for deriving the relation in the context of a single particle, we differentiate this relation. Angular momentum is the cross product of the perpendicular distance from the line of action of linear momentum and the linear momentum with respect to time. So we'll differentiate this formula here, this relation here. Okay, so we'll see now we are differentiating this relation. So this is the left hand side, differentiation of angular momentum with respect to time, and the differentiation of cross product of R and P with respect to time. So if we just apply the distributive property for the cross product, we will get here dl upon dt is equal to, here it is dr upon dt. See that actually not distributive rule here, we are just applying the product rule of the two vectors. So we will just product rule of two vectors. As I told you, I have given the formula in the mathematical tool. This is d upon dt vw. So first of all, we'll take the differentiation of one quantity, one physical quantity, then the another physical quantity remain as it is, then sum, after that the differentiation of the other physical quantity, that is dv upon dt, and this is the first quantity will remain as it is. Okay, so this formula I have given to you in mathematical tools. The same way we will apply the formula here. We'll just differentiate suppose r first, then p will remain as it is, plus will differentiate p and r will remain as it is. This is okay, this also I am just writing in the vector form. So now you will observe here dl upon dt, and this is p dr upon dt. Okay, this dr upon dt, you will see that dr upon dt we can write as v here. So this is v and this is r cross dp upon dt. Okay, now you will see that dl upon dt, and this is p cross v. P is also mass into velocity, and this is also velocity here. Okay, so what we observe here, that the product of, this is the cross product of same quantity, v cross v. V cross v, that means the theta will be 0, so sine 0 will be 0, and so that this cross product will come 0. Okay, so what we will find here, this is mv cross v can be written as mv square sine 0, because v and v, this both velocity will be having the 0 degree between each other, so sine 0, and ultimately it will come 0. So the first term of this equation will become 0, and only the second term will remain here. Okay, now you will see that dl upon dt, this is equal to r cross dp upon dt. Here you will see this dp upon dt is the rate of change of linear momentum, and which is given here as a force by Newton's second law of motion. So we'll just apply the Newton's second law of motion. We know that by the Newton's second law of motion, this dp upon dt can be written as force. So here we'll replace the quantity dl upon dt is equal to r cross, and in place of dp upon dt we'll write here f. So what you will observe here, dl upon dt or differentiation of angular momentum with respect to time will give us cross product of r and f, and which is the new physical quantity which already we have seen, that is tau, and you can say the torque it is. Okay, so we'll replace r cross f by tau here. Okay, so what you will find, this relation dl upon dt, differentiation of angular momentum, will give us torque. This is the relation between the angular momentum and the torque. Okay, thus the time rate of change of angular momentum of a particle is equal to torque acting on it, and this is the rotational analog of the equation, just the rotational analog of the equation f equal to dp upon dt. If you just carefully observe this equation, in place of f you will find tau, in place of p you will find l, and already we have seen that the tau is the rotational analog of force and l is the rotational analog of p, and this relation is the rotational analog of this relation. Okay, so which expresses Newton's second law for the translational motion of a single particle. Conservation of angular momentum. Conservation of angular momentum, in which we will see that the total torque, if we talk about the total torque, tau, it is the sum of the internal torque plus the external torque work on the system, and we know that the tau internal would be 0 just by Newton's third law of motion, as every particle apply the force on another particle in the same magnitude. So we have seen that all the internal forces would be 0. The similar way all the torque, internal torque, would be 0. So overall the torque which we applied on the system of the particle is the external torque. Now if the external torque will be 0, in such situation we know the relation between the angular momentum and the tau, and this time this tau is the tau external here. So if it is 0, this would be also 0. This relation dl upon dt would be 0. So obviously we'll see that this L would be constant. So we can say here, if no external torque is applied, so the angular momentum will be conserved. That means we can say here, thus if the total external torque on a system of particle is 0, then the total angular momentum of the system is conserved and that remain constant. This statement can be considered as the same statement, or this equation is considered is the rotational analog of the equation that dp upon dt is equal to 0 and p is equal to constant. That is the conservation of law of total linear momentum for the system of particle, and it has application in many practical situations. We shall look at a few the interesting application later on in this chapter. Example 7.5. Find the torque of a force 7I cap plus 3j cap minus 5k cap. That means it is given here the force is 7I cap plus 3j cap minus 5k cap. About the origin, the force acts on a particle whose position vector is I cap minus j cap plus k cap. So position vector is given here I cap minus j cap plus k cap. Now we shall use the determinant rule to find the torque, that is r cross f. So tau is equal to r cross f. Now we'll find out by the determinant. The tau is equal to, we'll write ijk, and the r, that is 1, minus 1 and 1, f, it is 7, 3 and minus 5. Now we will apply the formula here of the determinant, that is tau equal to aybz minus azby I cap, azbx minus axbz j cap, plus axby minus aybx k cap. So tau is equal to, I have written here just by multiplying it, aybz, that is minus 1 and minus 5 multiplied, that will come 5, and azby, it will come 3 into 1. So 1 into 3, this is minus 3, so 5 minus 3 I cap here. azbx here, azbx, that is 1 into 7, here 7, and minus axbz, ax is 1 and this is bz minus 5, 1 into minus 5 is minus 5, this minus will become plus, then minus minus will become plus, 7 plus 5 j cap. Now axby, that is 1 into 3, 3 here, and minus aybx, ay minus 1 and 7 minus 7, and already minus sign is here, this is, so it will become plus 3 plus 7 k cap. Now the tau will come here, 5 minus 3, that is 2 I cap, plus 7 plus 5 is 12, j cap, 3 plus 7 is 10, k cap. Okay, so here we have now found the torque of a force 7 I cap plus 3 j cap minus 5 k cap, and the position vector I cap minus j cap plus k cap as 2 I cap plus 12 j cap plus 10 k